For the last few years, AI in software engineering meant text prediction. You wrote a function, and the system guessed the next line. But true agents actively change an application's control flow. If a large language model is constrained by hard-coded loops and static statements, it remains a tool. It becomes an agent when it has the autonomy to evaluate a system, make decisions, and execute non-deterministic workflows independently. Claude Code functions as a terminal-based agentic operating system designed to navigate and manipulate software architecture. It operates on a continuous four-step mechanism: explore the codebase, plan the architectural changes, code the solution until test pass, and commit the result. Operating at an enterprise scale requires moving beyond standard natural language prompting into programmatic context manipulation. This matrix represents Anthropic's 45-chapter masterclass blueprint. It is the roadmap for understanding how these agentic systems operate. Moving from left to right, we map the progression from isolated local file navigation all the way up to orchestrating complex multi-agent clusters. Mastering this blueprint marks the threshold where a developer stops manually typing syntax and starts orchestrating AI fleets. To understand how Claude Code works, we start with how it reads your project. It bypasses heavy vector embeddings entirely. Instead, it relies on standard terminal commands like grep and dynamic file lookups to find exactly what it needs. This terminal-based read and write approach means your codebase stays local. There is no need to upload your proprietary architecture to an external database. Because it reads raw files, the system must budget its tokens dynamically. Activating its internal planning mode forces the agent to map out the structural change before writing a single line, preventing premature execution. Look at this equation. The primary bottleneck is a finite context window. As context grows, computational cost scales quadratically. When tokens exceed the trigger threshold, the system purges older tool uses, while keeping core workspace discoveries intact. This enables progressive discovery. The agent uses standard terminal tools to trace dependencies strictly as needed, rather than trying to ingest a monolithic repository all at once. Engineers can intervene using manual context commands to explicitly link or unlink specific modules, tightly focusing the agent's attention budget on the relevant logic. Success with these systems requires ruthless, programmatic context management rather than conversational chat. Once the agent finds the right context, it needs explicit boundaries. Wrapping instructions in XML tags and enforcing strict JSON schemas eliminates the ambiguity that causes models to hallucinate. This structured framing dictates how the agent handles multi-file architectural transformations and autonomous root cause debugging. It forces the output to match your exact pipeline requirements. A single session isn't enough for enterprise development. We use active context engineering to enable cross-session learning over long development cycles. By granting the agent access to memory tools, it can write and edit persistent Markdown files. It learns your debugging patterns and builds a team-specific code quality knowledge base that carries over to the next session. Even with memory, throwing a massive monolithic goal at the system will trigger API rate limits or trap the agent in an infinite reasoning loop. The solution is strict task decomposition. The agent must be forced to break large goals into atomic, independent tasks tracked meticulously in a local file. Here is the multi-agent coordinator configuration. A central orchestrator routes isolated context windows to specialized subnodes: a researcher, a coder, and an evaluator. The evaluator detects a syntax error and loops data back exclusively to the coder, preventing context pollution between different agents. This orchestrated, multi-agent approach is exactly how teams deploy full-stack production APIs and run continuous quality hygiene testing across thousands of commits. Decomposing tasks and isolating context is the architecture required for achieving continuous, autonomous execution without human bottlenecks. To make these agents interact with your databases or external services, you have to connect them. But writing custom tool calling code for every new integration is fragile and fails at scale. The industry solved this with the Model Context Protocol, or MCP. It is an open standard that separates tool orchestration from the non-deterministic reasoning model. This flowchart shows how MCP operates. A reasoning engine sends a JSON payload to a deterministic MCP server connected to an external database. Look at the vector database injecting only 3 tool schemas. Loading thousands of tools instantly exhausts the context window. Instead, MCP relies on semantic embedding tool search. It dynamically registers only the specific tools required for the immediate query, keeping the attention budget clean. Because the agent only sees what it needs, clear, explicit tool JSON schemas drive its behavior far more effectively than bloated system prompts. This standardized, heavily restricted access allows agents to autonomously hunt memory bugs and map threats inside isolated Docker containers without compromising the host system. Exposing strict deterministic APIs to non-deterministic agents via MCP provides the framework for safe automation in production environments. When you scale these capabilities across an entire engineering organization, the economics of resource management dictate your operational speed and your total cost. We optimize this by using speculative prompt caching, which warms the cache during human input to drastically cut latency on repetitive, high-frequency tasks. We achieve stateless horizontal scaling by moving session history out of local storage and into external cloud memory stores, allowing any agent to pick up exactly where another left off. Watch this singular beam splinter into parallel streams. This represents the system forking disk history to spawn simultaneous execution pathways across different Git work trees. At the enterprise level, deployment relies on zero configuration binaries, instantly pushing these agentic capabilities to thousands of engineers. Teams build institutional capacity by sharing standardized scale directories via central Git repositories, ensuring every agent understands the company's specific deployment protocols. Administrators track the exact return on investment by monitoring token usage and cost per task metrics through central admin APIs. The daily operating procedure shifts entirely. A single developer now orchestrates multiple agents simultaneously across decoupled branches, reviewing pull requests generated entirely by the machine. Safety is maintained by enforcing cautious mode on any destructive command, while automated classifiers handle read-only operations instantly without human friction. This shift moves the developer into the role of orchestrating parallel AI fleets rather than manually executing syntax. Transitioning to elite-level development requires abandoning rigid orchestrator frameworks that try to control every variable. The entire curriculum collapses down into three foundational pillars. The first is building with composable primitives connected securely through the Model Context Protocol. As the middle pillar pulses with our token threshold equation, we see the second foundation, engineering active memory and ruthless context management. The third pillar is mastering the continuous explore, plan, code, and commit agentic loop. Your success with these systems is determined entirely by how tightly you scope your tools and how clearly you guide the reasoning engine. As these geometric blocks snap into permanent alignment, the reality becomes clear. The era of autocomplete is over. Engineers now design the systems that write the code.